in this video series, you are going to be introduced to the principles of carbon-carbon bonds formation. So this learning unit will introduce you to a principle of retrosynthesis, where we can identify the starting materials of a product using the retrosynthetic procedures. Okay, for general strategy, normally synthetic planning starts with the product, which is fixed and unchangeable, and the art of planning the synthesis of the target molecule is what we call as retrosynthetic analysis. If you look at the equation here, Z represents the product, while X and Y represent the starting material. In this case, if this retrosynthetic analysis is represented by this arrow. This arrow is what we call as retrosynthetic arrow. This also arrow means it is from, from. So in this case, if you look at the question, Z from X plus Y, meaning product Z is made of X plus Y. And then this retrosynthetic arrow means a backward arrow used to show a retrosynthetic step. And then we have what does it mean by retrosynthetic analysis? So retrosynthetic analysis is where we analyze a target compound or a product, and then we think of how we can make it in the lab. If you look at the example here, the first one is the formaldehyde. This compound has a moderate complexity, meaning you can see quite a number of functional group in here. You can see there is an ester, there are also alcohol, and there are also amide here. So let's think, how can we make this compound? And then another second compound is the taxol. So taxol has higher complexity compared to formaldehyde due to the presence of more functional groups in the compound. So in this case, you can see alcohol, you can see amine, you can see ester, you can see double bond here, and then you can see ketone. Then you can also see heterocyclic compound. So these two molecules, they are derived from natural sources and also exhibit high biological activity. And if you look at the first compound, even for a molecule with moderate complexity like formaldehyde, it is not easy to imagine a complete synthesis from scratch. If we look at this compound, how are we going to start in order to synthesize this compound? So the best way is to start from the target molecule and then work backward with a series of disconnection until we get back to the readily available starting material. Sometimes when we disconnect a molecule, disconnect a product, we get a starting material, but that starting material is not available because it is still a big molecule. So we need to chunk it down into a smaller molecule to get so that it is available starting material. And this whole procedure is what we know as retrosynthetic analysis. Okay, in this learning unit, so you are going to be introduced to different terms, which is very important in this learning unit. So there are 1, 2, 3, 4, 5, 6, 7 terms here. And the first one is the target molecule or TM. Target molecule or product. Okay, so these are the molecules that you want to synthesize. And these compounds are usually natural product or bioactive non-natural compound. The second term is retrosynthetic analysis, which involve the process of breaking down a product or a target molecule into possible starting materials by breaking bonds. Okay, so this bond that will be broken will be created during the forward synthesis. Forward synthesis is the normal reaction synthesis that we always do, yeah? Okay, the third one is disconnection. So what does it mean by disconnection? Disconnection refers to the imaginary cleavage of a bond to split the molecule in simpler fragments. So let's say you have, this is a product. It is consists of 4 pieces, for example. And then when we do disconnection, we want to disconnect like this. Okay, so we have 4 smaller fragments. Okay, so this the lines here where we split the molecule is what we call as disconnection. Another important terminology is a functional group interconversion. So this functional group interconversion involves the process of converting one functional group into another, usually to facilitate a disconnection or to protect a reaction group. And this usually achieved by performing reactions such as oxidation, reduction, addition, or elimination reaction. For example, you have a ketone, for example, or a ketone or aldehyde, for example, yeah? You have this compound, aldehyde, for example. So you want to convert it to alcohol. Okay, this is the alcohol. Okay, when you want to convert, the conversion is what we call as FGI, or functional group interconversion. Okay, and then term number 5 is reagent. Reagent is a common term that you have encountered uh, since you are in school. So reagent means a compound that reacts with a substrate to effect a particular chemical transformation during the synthesis. Then another important term is what we call as synton. Synton is a generalized and frequently imaginary fragment, or usually an ion or radical that is produced by a disconnection operation. Okay, just now when you have a disconnection like this, so when you have disconnection, it gives you smaller fragment here. This smaller fragment is what we call as synton. Okay, and the last term is synthetic equivalent. Synthetic equivalent is the real chemical equivalent of a synton. Okay, synton is imaginary fragment, while the synthetic equivalent is the real chemical equivalent of a synton. Okay, now let's take a look on the principle of bond disconnection. Yeah. Okay. When we talk about organic reaction, there are 2 types of reaction. First one is the polar reaction. So polar reaction involve reaction with nucleophile and also electrophile. Then another type of reaction is what we call as radical reaction. So radical reaction usually happen to alkane group of compound, and it involves single electron species reacts with neutral acceptor. Okay, in polar reaction, it normally involves either heterolytic cleavage. Okay, this is polar reaction. While radical reaction involves single electron species. If you look at single electron species, it refers to radical, which also means the homolytic cleavage. Okay, When we look at the carbon species, there are many types of carbon species. This is a stable neutral carbon. When it has when it lacks of one bond, it becomes carbanion. When it only has one electron here, it becomes radical. When it lacks of two bonds, it becomes carbene. And when it has plus charge, it becomes carbocation. Okay, in acid-base chemistry, we normally encounter like this molecule. When it loses one bond, it becomes minus. So when it is minus, it is normally a base. Okay, now when we have a charge plus charge, so it normally become an acid because it is plus charge. And then we have also organometallic chemistry, where you have learned it in the previous learning unit, which is learning unit 2, the Grignard reaction. Okay, these organic chemistry are usually forming relatively stable complex, which M refer to the metal. And you know that when metal is bonded to the carbon, it is normally called as organometallic. Metallic refer to the metal, organo refer to the carbon. Okay, when we talk about disconnection, most reaction they are polar, and that's why when we disconnect, we will get two pair of synton with one positively charged and one negatively charged synton in each pair. And one pair of synton are usually much better than the other because they are obvious real synthetic equivalent on one case but not the other. Okay, for example, you have this target molecule. Okay, when you try to disconnect the molecule, what you get is, okay, when you disconnect this molecule, so this bond is now no more. Okay, so you can see this fragment and then this fragment. Okay, this is minus, this is plus. Okay, when you break a bond, one part become negative, one part become positive. And then you can also have another possibility, which is this part is negative charge, and then this part become positive charge. Okay, we take a look at the first pair here. Okay, we take a look at the first pair. So this pair, because it is plus, it needs something minus to balance it. So you add Br to it. And then this is minus. So in this case, it is actually CH2 minus. When it is CH2 minus, so you need something positive to neutralize the molecule, so it becomes CH3. So this is CH3. Okay, let's take a look at another pair. Okay, when we have minus here, so this minus can be compensated using MgBr. And then if this is plus, you need something minus, so it will give you an epoxide like this. So to summarize, target molecule, it is obtained from synton, which represent the synthetic equivalent. Okay, this is an example of how we do retrosynthetic analysis. For example, if you have this compound, There are three ways where you can make this compound. The first one, the second one, third one. Okay, so if you look at the first one, okay, it is a reaction between a ketone and Grignard reaction. Okay, the second one, it is a reaction between ester and Grignard reagent. You see, when you have ester reacting with Grignard reagent, you will get 2 moles of Grignard reagent. And then the third one, when you have Grignard reagent react with ketone, so this Grignard reagent coming from alcohol. Okay, this alcohol coming from double bond here, alkene, yeah. Okay, so this ketone also can come from the alkene. Okay, now let's take a look at another example where you have alcohol here. Then how are you going to make this alcohol? Of course, using Grignard reaction. So this alcohol, it can be made from aldehyde. This one, aldehyde. So aldehyde can be made, this cyclic aldehyde can be made from aliphatic dialdehyde, which then can be made from cyclohexene. Okay, so this alcohol can also be made from ester or aldehyde, and it comes from a reaction between Grignard reagent with CN or CO2. Okay, don't worry too much about this. I'll show you more example on the next video. Okay, so this is how functional group interconversion can be done, and usually you always use the recognized functional group relationship, and some complex molecule may contain more functional group compared to the simple molecule, and many of these can also be prepared from a carbonyl containing functional group. Okay, for example, hydration of double bond. Okay, we have double bond, and then we want to turn this double bond into OH. So we can do FGI. Okay, when we do FGI, once you get this, and then you disconnect this part. You disconnect this part, so you get two fragments here. One is the negative, one is the plus, and then this negative is now from CH2 minus become CH3 here, and then the plus here, when you want to convert it into a synthetic equivalent, it become double bond and H become benzaldehyde. Okay, and then please note that if you do FGI, normally the OH at this part, not this part, because when you learn LU3 before, this aldol is fit to this, but this one does not fit with normal reactivity pattern. Okay, so another example of FGI is also oxidation reaction, where you have an alcohol can be converted into aldehyde from oxidation reaction. So aldehyde can be further oxidized to carboxylic acid. So functional group interconversion can also be done from reduction reaction, where you have an ester. So this ester, when you reduce, it will give you an alcohol. So if you have amide, so when you reduce an amide, it will give you either primary or secondary amine. Okay, so this is the last part of this video, and we will continue on the syntone in the next video.